All right, so welcome again to our Mathworks mini-series. This is the third and final, for now, of this series with Mathworks. And we have some special guests joining us along with our friends at Mathworks, some friends from Blue Robotics. And we are really excited to have a co-presentation today from both. Both have been amazing supporters of RoboNation and our teams. And I just want to give them a massive thank you and shout out for their support, not only in the sponsorship that they provide, but really the support that they provide to you, all of you in the community. We know that you've got a ton of questions and that they're always there to help you out and answer your questions. Their dedication to competition teams and your progress and development and success means a lot to them. And for that, we are very grateful. So I will hand it over to Shubham to introduce himself, and before we introduce Blue Robotics as well.
Hello, everyone. Hello, everyone. My name is Shubham, and I work here at student competition teams at Mathworks. Mathworks is a leading developer of mathematical computing software for engineers and scientists. Today, we are partnering with Blue Robotics on this session. We have our founder and CEO of Blue Robotics, Rusty, here.
Do you want me to give an introduction?
Yeah.
So I'll welcome everyone. Thanks for joining today. Like Shubham said, my name is Rusty. I'm the founder and CEO of Blue Robotics. We started about 8 years ago out of my garage originally, with the mission of creating low-cost enabling components for marine robotics. And that's gone really well. Now we've got a company with 55 people and 220 products, and lots of cool stuff going on. Lots of cool student projects being enabled by some of our components, which is one of our favorite things to see. But we got started with this thruster that Shubham's going to talk about today. It's one of our most critical products. It's one of the first building blocks of any marine robotics project. So whether you're building an ROV or a boat or an AUV, you probably need to do some sort of system identification to model that thruster and get it into your system. So excited to hear from Shubham about how to do that in their software. And thanks for joining today.
Perfect. All right, so let's go ahead and get into the actual content. Shubham, you can go ahead and share your slides.
Okay. Hello, everyone. Welcome to this session on system identification of Blue Robotic Thrusters. Today in this webinar, we'll see how to generate mathematical models of a T200 Blue Robotic Thruster with the data provided by Blue Robotics team. We'll take a look at motivation and background required for system identification. Then we'll dive into different approaches for modeling with some software demonstration. And we'll see how we can use PID. We can use this model for PID controller design. And we'll take a look at some key takeaways. So a common scenario we see is where we have a new piece of hardware and we probably want to design a controller for that. And a good way to do it is by modeling it. Today we'll be modeling Blue Robotics T200 thrusters, which is commonly used in maritime competitions. Now, you can pull all the modeling types on the spectrum. First one we have is the equation-based modeling, the first principle modeling, where you write down the equation and determine what is exactly going on in the system. Then you have black box modeling approach, which is more of a data-driven modeling, where you take your input and output data and generate a model. And in between, you have gray box modeling, so where you know the equations of the system, but there are some parameters which you're not quite sure of. So for example, in a suspension system, you know there is mass, damper, parameters, but you don't, sorry, in suspension system, you know the geometry, okay, but you have to still estimate the parameters of mass and dampers. So we'll be using system identification to create a model from input and output data. So system identification is the method of finding mathematical data of a system using input and output data. So what we do is first we excite our system with some input, which cover different behavior characteristics of the system, and you record what's the output. Then we choose a model structure, which basically describes the relation between input and output. So, and there's wide range of models that you can use to estimate your model. So first one, some of the simple model structures include transfer function model, state space model, and then depending upon your requirement, you can move to like more complex model like nonlinear models. Let's take a quick look at software demonstration. Okay, here we have our data in CSV format. So we have our sine sweep data and square sweep data. The reason we have our data in this sine, square, and square sweep format is because we want to so while giving the input, we want our system, we want to excite as many frequencies as possible to get a proper response from the system. So we have our data in CSV format. Let's take a quick look at it. So if I run this, yeah. So here you can see I have the input sine wave here and the response of the thrusters for the sine sweep. Similarly, for the square sweep, I have a input square wave and the response of thrusters. Now you can let's clear all the variables. Okay, so we import our data. So we have our square data, we just drag it and import it. Now we specify the name. So let's put it as input square, and this as force square. Okay, so we'll select the data, select the option as column vectors because we want them to be like individual columns. And to remove this input and output NaNs, we'll select exclude rows with, okay, and we'll import our selection. Okay. Similarly, we can do the same thing for our sine data. Okay. Okay, so we have our input data and our output data. Now, to perform system identification, we'll be using a system identification app. So here under apps terminal, you'll have a system identification app. You open it. So this is the app. On the left-hand side is where you import your data. So your data could be in time domain, frequency domain format. On the right-hand side, you have all your generated models. Once we generate the models, they will appear here. Here we have our pre-processing options, okay, whether we want to filter the data, so do some pre-processing operations. Here, here is where we select the model structure we wanted. Like here we have transfer function, state space. And so let's import our data. So our data is in time domain format. So So our input data is input square and force square. Let's name this as square data. Our start time is 0 and our sample time is 0.002, as it's in the data. It's our sample type is 0.002. Okay. And let's import it. Similarly, we input our will import our sine data. I think I have named it wrong, so it's input sine. Okay. So now we have our square data and sine data, and so if you want to select when you select a data from it, it will appear in bold. Okay. So now if you want to see the time plot, we just click here, click a time plot. Okay, and we see it this way. So if I just open the square data, okay, you can see here, this is the input sine input wave, and this is the response of our thrusters. Okay, it's a little bit noisy. So we have our pre-processing options as well. As the data is noisy, let's start with some simple options. Like let's start with removing means. So we'll drag our square data here, remove the means. Okay. Now we have selected our this square data, which is where we have removed the means. Now, if we see the time plot, it's close to 0. Basically, what removing mean does, it's normalizes your data and centers it around 0. So we select both of these and we take a look at it. You can see that we have removed the means and centered our data, which is in red, around 0. So similarly, we'll do this for our sine data. Okay. So once we have pre-processed our square and sine data, we'll estimate a model. So let's go with a simpler. Let's start simple. Let's select state space model, and we want our validation data to be our as our sine data. And yeah, so when you select estimate state space option, here you specify your model name. Okay. Model order is basically the complexity of a system. Okay. Here I'll let the app choose the best value for me. Here you can give the range from 1 to 10. Okay, and you can see here that on this chart, it's recommending me a model order of 4. Okay. So estimate it. So I'll just go with the recommendation. Okay. So once we have the model, I think I made a mistake. Hold on. Let's just delete this. Okay. So once you have your data, which is removed from which is pre-processed, okay, we'll select our square data as our working data. Okay, and this sine data as our validation data. Then we'll select state space model. Okay, and we'll pick the best range and we'll estimate. Okay, and once we have our data, so once we have this, we'll click the model output. It will show me that my model output has an accuracy of around 77.996%. So which is not that great. Okay, so you can see here that the data is very noisy and it's struggling to fit our state space model. It can definitely be improved. We'll start by removing the noise from the data. So we again select our square data, put it in the workspace, and select a filter. Okay, so now this is where knowledge of your systems comes in. This is where your knowledge of system matters a lot, because for the thruster we know that the noise lies mostly in the higher frequency range. Okay, so either you can specify the range here manually. So either here you can specify the range, or you can just select it using your cursor. So let's select it, and once you have selected, we'll click filter and insert it. So now we have our filtered data here. Similarly, we'll filter our sign data. So once we have both the data filtered, so we'll put our filter data in the working data space and sign data in validation data. So let's do the state space model again. Okay, so okay. So if you see the state space model which we have generated after filtering the data, we can see that the accuracy is around 91%, which is pretty good. Okay, and similarly, like similarly, if you want to like estimate a transfer function model, okay, so you just put your sign data here, select transfer function models, and estimate. So you specify a name here, and you need to specify poles and zeros. Okay, so here I'm selecting poles to be 2 and zeros to be 1. Depending upon the performance, we can change the poles and zeros accordingly, and click estimate. Okay. So yeah, here we can see that our transfer function accuracy is around 90%, which is really good. And once you have your models, okay, you can export it to your workspace. Okay, just click it and drag it to this button to workspace. Okay, similarly, we'll import our transfer function, and we don't need this model, so we'll just delete it. Now here you can see that we have imported our so we have our state space model and transfer function model. So if you open this, you have your all state space matrices A, B, C, and D. Similarly, in the transfer function object, you have your numerator coefficients and denominator coefficients. Now, once you have your model, okay, let's see how we can apply a PID controller on it. So I have this model of where I have a reference signal generator, okay, then a PID block and a transfer function block. So you can just double click on a Simulink workspace and select transfer function model. Okay, once you have, so the thing is, yeah, it changes the inner numerator denominator y by s. It changes when you specify the values or when you zoom in or zoom out. So once you open it, okay, and we specify the numerator coefficient. So here I just specify my object df1 dot dot numerator. And similarly, let me check the name. Steve1. Okay, similarly, I'll specify it for denominator. You can see here that select. Okay, so once I have the denominator, okay, I have a PI. So we import a PID block. Just what is it? Type in PID in your Simulink workspace, and you'll open up, and you'll get this block. So let's run it. Okay, so we see that the block is tuned. That's why the response is means it's really good. Okay, so so we have a desired step response, and we're getting like a good error rejection. Now I'll show you how to do it, like how to tune a PID controller. So I'll delete this block. I'll open up the PID controller block and just attach it here. Okay. Okay. So let's run this. Let's run this. Open the scope. So this controller is not tuned. Okay, so we haven't tuned the PID gains and response accordingly. So we can see that the error rejection is not that great. So manually tuning your PID gains can be very time consuming, and it might not be that perfect also. So here, if you double click this block, you have an option to tune your PID controller. So we'll be using PID tuner app to tune our controller. So if we hit tune, so it will linearize the plant model first. And depending upon the response that you want, so let's say you want your response time to be faster, so you can just select it accordingly. And your transient time, you want it to be aggressive, so you can just adjust it here. And to see the gains, you can click show parameters, and it will show you the gains of the current tune system, and the gain of the block that is currently running. So here you can see the rise time, settling time, and depending upon your performance requirement, you can tune your control. Means it will tune the controller. So I'll just select it for here. Then once you have your response tuned, you update the block. Okay, so you can see that the block line is gone. So this will be our current block response now. And you hit OK, and once I run it, yeah, you can see that our actual so this is our desired signal, and our controller is driving error to the 0. Okay, so so that's how you can like import your state space model, put a PID block, and if you want, we can even adjust the reference signal accordingly. And yeah, it will still give you a good response. So yeah, so let's take a quick recap at the system ID workflow. So first you collect your data. Okay, your data is in such a format that it captures the behavior of the systems. Then you pre-process your data. Basically, you'll normalize your data, and then you'll apply some filters to remove the noise. And once you have your pre-processed data, you split it into the validation data and another set where you estimate your model. You select your model structure and perform system identification. So here we have used state space and transfer function, and estimated the model. And once you have your model, you evaluate it, okay, with using your validation data. So depending upon the validation, depending upon the evaluation, you either if you're not satisfied with the evaluation, so you go back, you collect your data, okay, then you pre-process it again and change the model structure, okay, and that's how you iterate and decide which model is better for you. So some of the key takeaways. First one, definitely have a good data that captures the complete system response. Start with some simple model, okay. Your models should be complex enough to capture the behavior of the system, but not too complex, okay. And depending upon your performance, you can increase the complexity of the model. Always have a validation set when you pre-process your data. You should always keep some data for validating your model. And once you develop, once you are generating your model, you should iterate and see which model gives you better performance, either transfer function, state space, or some other type of model structure. When you are modeling a bigger system, okay, then it's generally good practice to model smaller components and integrate it into a larger system. And we saw how we can import our generated models into Simulink, and how we can auto-tune our PID controllers. Okay, and so we have some on-ramps. We have some really good on-ramps that will get you started with MATLAB and Simulink. And apart from that, if you want to learn like another technologies like deep learning, control system optimization, we have really good on-ramps that will get you to speed. And apart from that, we have tutorials and videos that are dedicated to just student competitions. So we have tutorials on aerospace, automotive, robotics, modeling, computer vision. And similarly, we have a student launch blogs where we post new technologies, student success stories. Okay, the Mathworks software is free for RoboNation competition students. So if you go on this link, I'll ping down the link. You request a software, and we'll send you the license that. And if you have any questions, you can always mail us at roboticsarena@mathworks.com, or you can even post a, or you can always post your doubt on our Facebook group, Robotics Arena. Okay. Thank you for joining. Please let me know if you have any questions.
Thank you so much, Shubham. Does anyone have any questions or troubleshooting that you'd like, burning questions, especially for Mathworks and Blue Robotics here at the same time? It's kind of a unique opportunity to get your questions answered. And for those of you who are watching this on recording, I know there's several of you. I know that as Shubham said, you can always email and ask those questions. And I know that Blue Robotics has a great customer service line as well, and get back to you all really fast. But does anyone currently on live have questions that they'd like answered? You can put them in the chat, or you can just take yourself off mute and ask your question live. Anyone, don't be shy. This is an amazingly unique opportunity for you right now. And I'm sure we'll have another chance to do this again. These are sessions that we want to keep doing with our partners so that you guys can keep learning and we really start building up that library. So this is the first of many, I am sure, to come. Any questions? Technical, non-technical? Yay. Andre says, Shubham, I'm learning so much. Thank you for doing this.
Oh, thank you.
I am also learning a lot, but admittedly, not as much, I think, in terms of implementation. anybody else have any questions? Anything to say, share? I know that our friends at Blue Robotics have had some really exciting news lately, and I didn't know if you all wanted to just chat about that real quick. If you're prepared, I know I'm just sort of ad hocing here, Rusty, but we follow you a lot on social media, and of course, you know, all of your announcements that you put out, and I've been really excited. So I thought I'd maybe give you this opportunity to chat a little bit about some of the new things you've been doing.
Sure, absolutely. So thanks for the hints. The big thing we have coming out that is very much related to this guide here is that we've got a larger thruster. We've had the T200 thruster for years. We've got a larger thruster called the T500 thruster that's going to be coming out very shortly. Like you'll hear about it in a week or two. And so we're very excited for that. A lot of these same principles would apply to that, absolutely. And we do hope to and expect to see it on a lot of competition vehicles in the future as well. Maybe especially on those Robot X vehicles that are a little bit bigger. So we'll also have some other exciting news on our website, some product updates to our ROV and enclosures and things in the next couple of weeks. So just keep an eye out if you're interested. Yeah. You're muted. Janelle, you're muted.
Thank you. That's very exciting. I was just saying, very excited to hear more and to be looking forward to those announcements. So make sure you follow them on social media. Rusty, your handles are?
Blue Robotics.
Mm-hmm.
Everywhere you get your social media.
Yep. On all the platforms. And then if you have any questions for the RoboNation team, you can always reach us at autonomy at RoboNation or on the vBulletin forum. And also make sure you register for our next Tech Talks and community hours. And those are listed right there. So if no one has any other questions, comments, anybody, then we will wrap things up here, and I will stop. Oh, we do have one question that says, Rusty, about how long does it take to develop a new thruster concept to release?
That's a good question. It varies a lot. So the first one, the T200, we spent like 6 or 8 months developing. And of course, it was just me and my friend in a garage at the time, and our expectations, we didn't know that much about product development. Our expectations for what we needed to accomplish were not that high. We just needed to get something out the door, like try to start this business, see if people are interested. Now for the T500 thruster, we've been working on that one for years. Like I think we started talking about it like 5 years ago. And things have changed a lot since we have so many more customers now and people who count on us. The bar is much higher, the expectations are much higher, so the diligence that we put into a new design is like so much higher than it was back at the beginning. And every time we do a new development, it kind of follows that way. The company evolves, our customers evolve. They're looking for newer and better and higher performing things, so we've got to keep achieving that. So the answer is it varies. You can do it quick, or you can take a long time and do it. Depends what your customers need and what you're trying to produce. It's definitely not super fast. It's always a lot of work. Good question.
What are some of the things that you all do in your testing and design cycles that are kind of similar to what our students are going through? And what are maybe some tips, as you mentioned, like with developing the T200s, that it was different? And I imagine as you have grown and learned, there are things that you have learned by mentorship, but then also just through the experience itself. And are there any things that you would share with our students that might help save them some angst or time?
Yeah, so I'll talk about the things that are similar and then the things that are different. So on the similar side, we go through a lot of the same iteration, design, brainstorming, making CAD models. Usually the first prototype of a product, we just hack together from parts we have or 3D prints. It's pretty rough. And What I found with that's how I did. I was on a competition team in college. That's how we did it. And the difference, I think, is when you're at a company, you've got to see the project through longer, and you end up having customers, and you're not just building one of these things anymore. You're building it over and over and over again. And there's a huge amount of work that goes from having one of your system and just having it work to having lots of your system, and they all work and they're all reliable and all of your customers are happy. So, kind of in these competitions, you work up to the point where you've got a really solid prototype. You demonstrate that your vehicle is capable. And then what we do when we design a product now is we go from that and we validate that product with a lot of different samples. We have to validate our manufacturing line to make sure we can build it repeatably, and that not just the first one, but every one we produce is going to be good. And we've got to get it out into different customers' hands and make sure that they all have a good experience. So there's a lot of added elements that go on top of it compared to a competition vehicle, which you'll hopefully someday experience. And they're all fun. There's a lot that goes into it.
Thank you for sharing that. I imagine everything that you all have been talking about too goes into play in terms of modeling out everything and testing, and so this has been really helpful. Does anyone else have any questions before we stop recording and let you all go? Yeah, thank you so much everyone for joining us live today, and for those of you who are watching, don't forget that there are ways that you can stay up to date with things and ask these questions here at email, on the forum, and also of course by registering for our next Tech Talks. Thank you so much.